we'll go from current slide, and I may even turn on the projector. Do that. Now, there's these announcements you've heard, and then a couple more that you need to know about that don't affect you, but they do affect others. 1 week from today is the College Transfer Fair Day on the Birmingham West Campus, the Academic Building, B Hall, from 9:30 till 11:30, and they'll be all up and down the hall, main floor, the upper floor of the B Hall. Tables set up all up and down there, and a bunch of these universities and colleges will be represented there. Then 1 week from tomorrow, the 13th of February, from 9:30 to 11:30, they'll be here on this campus, in this building, somewhere around the campus cafeteria. I doubt if they're going to be in there. They say they will, but my guess is going to be in the faculty staff dining room, which is just next door, which no faculty staff usually eats there anymore, but that's what it was set up for originally. And they can get quite a few tables in there. I doubt if they'll get enough if all these people show up, so they may be out in the hall, maybe in the cafeteria too, I don't know, but check them out. Please go by and talk with some of the schools just to see what type of things they ask, what they're looking for, and maybe ones that you're planning to go to. Okay? You may find there's scholarships or other things available. The summer internship, 10-week internship that they pay you to go to, deadline for that is February 15th on the email, which is strange because that's a Saturday. 17th in the brochure, that's probably more likely. That's a Monday, but I wouldn't put it off. Please check into that because it's a fantastic deal. And they have others like that. Check out, you're both in either honors college or STEM or some of those. Excuse me, they keep track of a bunch of those experiences for undergraduate research experience. Now, the other thing, and again, this doesn't affect the two of you. Y'all are in good shape. But does affect, I think, one person in this class. I'll find out later today whether it really does or not. But I'm guessing it does, or did. But in case you know of someone who's in this circumstance or hear someone talking about it, usually at the end of the day, I do attendance for that day. We have to do it on the computer. And last Monday, I did it, no issues at all. Yesterday, end of the day, this is probably what I was doing, my throat got sore, I don't know. But I was, like I said, doing some stuff. And I was doing attendance, and one of the people, the first thing I noticed, that somebody who I had entered attendance every day, I mean, everybody I had from the beginning of the term, my attendance didn't show up in one class. And on the system, they're green when you haven't done them, they turn a beige when you have done them. And they were all green. So I went back to the first of the term and started checking, and all the attendance was in there till right down near the end. There was somebody who had been there, I had put his attendance in, it was completely blank. So what is going on here? So I had to put his attendance in for every day since the beginning of the term. Then I also noticed that somebody else in that class, seemed like one or two people, suddenly they weren't in the class anymore. I went, oh, they removed non-paid students. Now that's my guess of what had happened. And then that student, they either removed them by mistake and then had to put them back in but didn't have his attendance because they removed him, so I had to put the attendance back in, or else he had paid after they removed his name and then they put it back in. So then I went to the rest of my classes, and in a couple classes there were one or two people who hadn't paid, and they weren't on the roll anymore. So that's what I'm getting at. Both of you have paid, or all indications are you paid. You are, as far as I know, still on the permanent roll. But there's at least one person in this class who was not on the permanent roll, and it was rather much of a surprise to me that he wasn't. He's been here most of the days. So just a word to the wise, check Now, I don't know what happens if you're not on the roll. I know what happens if you're not on the roll, but I don't know how you tell. If you go to Student Suite and can't get in, or you go to Blackboard and you don't find anything there, you go to something and you can't do, that's probably the indication you may not be on the roll anymore. So check it out, and this is mostly for that person. So anyway, that's done. And then today also, I got an email that we were supposed to have done no-show reports earlier in the week. I hadn't done mine, so I did mine, and that's when I noticed that other people in Monday, Wednesday classes, there were a few, and that's when I noticed that he wasn't. Okay. Anyway, and then this morning, in my Cal 1 class, 2 people were here who weren't on the roll, but I didn't want to single them out, so I said, please check and see if you think you may not be. Check and see, because a couple of you aren't on the roll anymore, so, or you weren't as of whenever they did the no-show report. So anyway, enough of that. Any questions on anything we've done so far? All right. What we were doing last time, we had gotten up to the point of computing cross products. And they had shown a technique for doing so, which was a little convoluted, and I think I promised to show you an easier way, didn't I? Or to me it's easier anyway. So here's what we've got. U is a vector I minus 2j plus k. V is a vector 3i plus j minus 2k. Find each of the following U cross V. Do you remember how this is done? I'm going to get my pen set up first. Okay. U cross V. How do you determine a cross product? Remembering it is going to be a vector. A determinant. Remember, didn't I introduce that word to you last time? What goes on the first row of that determinant? I, j, k. The unit vectors I, j, and k. Next. Okay, you put the one that's listed first next. And here's why. Cross products are not commutative. If you change the order, you change the value. Okay? Actually, what it does, it flips it over. Okay? Because cross products are a right-hand rule. If you do them the other way, it flips it in the opposite direction. So, you put the components for U under the unit vectors that represent those. And then what does that be? 1, negative 2, 1. Okay? Next. 3, 1, negative 2. Now, what the book did was close that determinant. And in effect, that's what you're doing. But here is the easier way. Remember what they did? Remember they took the I and then did the cross product here, the minus of the, that. Here's the easier way. You don't have to keep up with which one's plus, minus, that kind of stuff. Here's the easier way, or at least in my mind it is. Repeat the first 2 columns. I, 1, 3, and J, negative 2, 1. Just repeat the first 2 columns. Now, this is not proper to indicate determinant, but I'm still going to do it, okay? Because determinants can only be taken of square matrices. This is not square anymore. But here's what you do. And this is, to me, so much easier than having to remember where to put the plus and minuses. You do your down diagonals. Remember, the down diagonals are always positive. So you do the down diagonals there, and what do you get? 4i. Okay? The next down diagonal gives you plus 3j. Next down diagonal gives you plus k. Okay? Okay. Now, your up diagonals are always negative. So I'm going to take out those just so it'll be easier to read. You could leave them in, but it makes it easier to read taking them out. Now I've got the magic pen so I can do that easily. Okay, y'all don't. Okay, never mind. Okay, the first up diagonal would be this way, but remember it's negative, so what would that be? Plus 6K. Perfect. Okay, next up diagonal? Minus J. No, that's an I. My writing stinks. You're making fun of my writing, aren't you? Okay, okay. Minus I. Okay. And then the next up diagonal is plus 2J. And now you just add them together. What do you get? 3I plus 5J plus 7K.
So doing it like that,
yeah.
What do you just repeat the first two columns? Does that work for all of these?
All when you're doing threes. Now if you're doing fours, nah. But we're not doing fours. We're staying in three space. You're going to be doing fours one of these days, but that's your problem. Okay. These, when you're in three space, this works every time. Okay. When you're doing cross products, and it's so much easier. You don't have to remember which is the negative position, and then is it plus minus. You know how you do. It just is straightforward like this. Okay. Let's see if that's the same thing they got. 3I plus 5J plus 7K. Good for them. I think mine was easier. Okay? Let's now do the B one. Okay, so I'll erase all this. And what would the B be? Vector V cross vector U is, what do I put where? I, J, K, and if you're going to do it my way, you can just go on and repeat the first two, IJ. Okay? You don't have to do it my way, by the way. Okay? And then what do you put next? 3, 1, negative 2, 3, 1. Got it? Okay. All right. And what would you do next? Yep. Down diagonal will give you I. That's yes in Navy speak. Okay. Minus 2J. Minus 6K. Negative K. Second? Really? Up diagonals are? Second? Negative 4I. And 3J. And then you get negative 3I, negative 5J. You're leading me astray, aren't you? Okay. Okay. J and negative 7K. Now what do you notice about that answer as opposed to the previous one?
It's all negative.
Exactly the opposite of the previous. What did you do? You reversed the sign. So that you reversed the order and that reversed the sign. And again, multiplication, cross products of dot products of two vectors, commutative. No problem there. Cross products not. You get the opposite of your previous answer, and that's what we got. Okay? Now, any questions on that? And hopefully the book got it too. Good for them. Okay? Let's see what the third one gives us. How would you do this? IJK. Want to go and do the IJ? Okay. Next. 3, 1. Next. 3, 1, negative 2, 3, 1, because you're crossing it with itself. Anyone want to make a guess now? We're going to do it. Let's do it.
0.
Yes, the 0 vector. Okay? It has to be a vector, and it will be the 0 vector. Because dot products in the same direction, you just multiply, okay? Perpendicular gives you 0. Cross products in the same direction gives you 0, and perpendicular you get the maximum that you could get. We haven't gotten that yet.
Write it properly, is it 0 with the arrow above it or the caret?
No, arrow, because you can't have a 0 unit vector because the magnitude has to be 1 and 0 is always 0. So, all right. So let's see, prove it to ourselves that's the case. This will give you negative 2i. This will give you negative 6j. And this will give you plus 3k. Next. Negative 3k. That's working out so far. This would be plus 2 what? I. That's yes and never mind. Okay, next. Plus 6j. Yeah. It gives you the 0 vector. Okay. 0i plus 0j plus 0k. Has to be a vector because the cross product of two vectors has to give you a vector. All right. Now, they're going to do it, like we said, a little differently. They're going to carry you through. They wrote it down the same, only they left it the square matrix, which is very proper to do. Okay, and then they did their cross products here. And again, you wipe out the row and column for the I. You're going to keep the I. And then you do your cross product here. 4 minus 1, it will be 3. So this is the determinant you have left over when you wipe out row and column. When you wipe out the J row and column, you have 1, 3, 1, negative 2. And wipe out the J row and K row and column, you get 1, 3, negative 2, 1. Okay? Then you do the cross product here. 4 minus 1 will be 3i minus 2. Well, this is a negative, so it'll be a minus 2 minus 3, that's minus 7, but minus that would be a plus 7k, and 1 minus 6 would be a minus 5k. 1 plus 6 is 7k. And see, the signs will, the only reason the signs are there is to reach out and trip you, okay? That's the only reason we have those, especially negative signs. They're just there to trip you up. That's what we get. And when you work it out, you get 3i plus 5j plus 7k. Now that's not that much longer than the way we did it. It just, to me, offers more opportunity for error, especially sign errors. But do it whichever way you have. You've got two techniques at your fingertip. Use whichever one you like best. The V cross U, you just reverse the order of the second and third rows from what we did before, and that gives you this. I won't go into gory detail with it, but you see that's your the matrix, the determinants you have as your coefficients there. And then when you work these out, it's 1 minus 4i minus the 3 plus 2j plus a minus 6 minus 1k, and that would be minus 3i minus 5j minus 7k is exactly the opposite of the reverse of the cross product. Always that's going to be the case. Okay, and then when you do the third one, hey, that's not very fair. They just said it's equal to 0, and it is. Later, Dawson will be able to tell you why when we get to that. Anytime you have a matrix that two rows or columns are dependent on each other, you're going to get a zero determinant every time. They didn't do any of the work, but they just said that's the result. Okay. Now, they hadn't given us that as a characteristic yet. They will right here. Here are the algebraic properties of the cross product. So let U, V, and W be vectors in space, meaning three-dimensional vectors. C be a scalar, any real number in the world. The first, U cross V, is not commutative. It's exactly anti-commutative. In other words, U cross V is exactly the opposite of V cross U. Dot product? No. U dot V would be the same as V dot U. Cross product, exactly the opposite. Now, how about our sort of distributive type properties? U cross the sum of two vectors V and W. Well, of course, this can happen because the sum of two vectors is a vector. You can do a cross with the vectors, and what you'd have to do is all that mess that we take. This is V1 plus W1, V2 plus W2, V3 plus W3. Do the cross product with that, and then and you'll see those come out the same. That is a nasty one to prove. I mean, it's not nasty, it's just hard to do. But what you get is U cross V plus U cross W. Do not accidentally reverse the order. You're not going to get the right answer. Okay? Now, distributing a scalar over a cross product, that means you just distribute the scalar over one or the other, it doesn't matter which. C onto U cross V is the same as CU cross V or U, don't change the order, U cross C. You can put the C with either one, you don't put them with both, either one. Now, U cross the zero vector, if this were dot, U dot the zero vector would give you the zero vector. U cross the zero vector or a zero vector cross U will both give you the zero vector. Okay? One thing cross products and dot products have in common. And then U cross U is the zero vector, whereas V or U dot U, what would that give? That was a dot product, not a cross product. Number 11. Magnitude of U squared. Okay? Here, 0. It's easier to remember. Now, here's another. This is a bit bizarre. It's dotting U with a cross of V cross W. Well, V cross W is going to give you what as an answer? A vector. You dot a vector with a vector, and you get a scalar. Okay? So you better get a scalar over here too. Now, what they notice here is you can, I don't know what you call this. You're exchanging the dots and crosses and changing your grouping. Yeah, so that would be U cross V dotted with W. Bizarre one, and I'm trying to think if I've ever used that property in my life, and I can't recall doing it. Maybe we'll run into a circumstance where you will need it. I can't think of one, okay? But it is true. And again, to prove any of these, you basically have to do your three-dimensional component, 3 components, and do the work on all of them and show that they all come out being the same. Yeah. Okay. Yeah, will take some effort. But maybe it's worth it. They proved property 1. We basically already did that. Okay, we showed that it worked, but then they proved that it did in the generic case. Okay, they didn't do the others, which can be a lot hairier. They'll probably have those for homework exercises. That will be neat, won't it? Okay, here's theorem 11.8. Some geometric properties of the cross product. Remember, there were some kind of geometric properties of the dot product that gave you your projections. Remember? Those were dot product. geometric properties. Okay? Here are some for cross products. Let U and V be non-zero vectors in space, meaning three-dimensional vectors. Let theta be the angle between U and V. Okay? Ha! Ryan snuck in. Now, I told the others this before you got here, so just in case you don't go back and listen to the first part of the YouTube video, let me say it for you too. A couple of things have happened this week that they usually do happen, but not this early. Okay? And the first of these are usually every day. At the end of the day, I enter attendance. I did that last Monday. Entered attendance was no problem at all. Then, at the end of the day yesterday, I entered attendance for my 4 classes I had yesterday. And in the first one, I had to go back and redo all the attendance because one person had his attendance taken out, and then I had to put it all back in. And I also noted there are a couple people missing from that class. That's a big class, 28 or so people in it. Okay? Then in at least one of my other classes, I noticed I was missing some people. I said, oh, they must have removed non-paid students. Okay. So I came in this morning, and they had that we were supposed to have done our no-show report. And that's the one that if we had a paid student who never showed, we were supposed to report that so they can take them out of the system too. And when I was doing that, the list they give me are only paid students. And I noticed in some of my Monday, Wednesday classes, there were some students who were not listed as paid. And they did not show up on the no-show report. Well, they weren't looking for them, they were looking for paid students. So, if you know of anybody who may not have completed all payment, they may not be able to get into the system. I don't know if they can or not. I don't have the student side, just to let you know. That has happened, okay? Usually it happens, but usually a little later in the term. It's happened now. Okay, so here's the geometric properties of the cross product. This is in Chapter 11, Vectors and Geometry of Space. We did Example 1 today. We did Theorem 11.7 today, and we're just about to do 11.8. That's where we were. And this is on page, this is 11.4, cross product of two vectors in space, page 781. All right. U and V is the two non-zero vectors in space. Theta is the angle between U and V. Okay. I think we've talked about that angle before too. It's usually the acute angle between the two vectors. All right. Now, this is always true. The cross product of two vectors is always a vector. We know that. Not only is it just any old vector, it's going to be orthogonal or perpendicular to both U and V. So U and V don't have to be perpendicular to each other. They could be acute, they could be obtuse, they could be whatever. But if you cross them, the cross product would be perpendicular to each other. So in other words, U and V, any two vectors are going to be in a plane somewhere, right? And the cross product is going to be perpendicular to that plane, always. Okay, so there's the first. Here's the next one. Now this looks a lot like a result we got from the dot product. When we had the dot product of U dot V, that was magnitude of U times magnitude of V times the cosine of the angle in between. Well, this isn't the cross product. This is the magnitude of the cross product of these two vectors is the magnitude of U times the magnitude of V times the sine of the angle in between. And that's why it doesn't matter whether it's acute angle or obtuse angle, because guess what? Sine is positive in both the first and second quadrant. And obtuse angle is in the second quadrant. Acute angle in the first quadrant, so not going to matter whether it's what angle theta you use, either acute or obtuse. You certainly don't use an angle beyond 180 degrees. Okay. Now, third geometric property, U cross V is the zero vector if and only if u and v are scalar multiples of each other. In other words, they're parallel, okay? Or technically anti-parallel, okay? If they're along the same line, you get a 0. That's why when you cross a vector with itself, it's parallel to itself, okay? So it's going to give you the 0 vector every time. And then, back the same as this, u cross v, now this is surprising, is the area of the parallelogram having u and v as adjacent sides. That's sort of a new take. I don't think the dot product had anything that was very close to that. Well, I was going to say it had something to do with area of the triangle, possibly, but this is the area. The magnitude of u cross v is the area of the parallelogram that has those two adjacent sides as adjacent sides. All right, so u cross v and v cross u are perpendicular to the plane determined by u and v. One way to remember the orientations of u, v, and u cross v is to compare them with the unit vectors I, j, and k. Okay? Boy, that's a kind of a run-on sentence, isn't it? The unit vectors I, j, and k equal I cross j. Okay? That's true, but that's sort of combining two concepts. So here's vector I, x direction, cross with vector j, the y direction, you get the positive k in the z direction. Okay? Okay, that's certainly true. So u cross v is going to be the right hand, your right thumb pointing in the direction of right thumb when you do the correct order, u cross v. Three vectors u, v, and u cross v form a right-handed system, whereas the three vectors u, v, and v cross u form the left-handed system. In other words, turn the right hand over and you're going down with u cross v, or v cross u. Okay. So I don't change hands. I just say do v cross u, and now you see it's going in the opposite direction of v cross v. Okay, here's example 2. Find a unit vector that is orthogonal to both u and v. How would you do that? Can you give me a vector? It doesn't have to be orthogonal, that you can guarantee is orthogonal to u and v. Well, oops. The cross product is always orthogonal to both, right?
So just do a cross product.
Oops, I'm going the wrong way, sorry. So first thing we do is do the cross product. U cross V. And guess what? It doesn't matter which order you do these, but what would that be? How do you do that? I, J, K, I, J. Now, Ryan, this is something I showed them earlier today. It's a little bit different from how the books had to do cross products. If you've had physics, you may have already run into this. What do you put next?
1, 4, 1, 3, 4.
Okay.
And then 2, 3, 0, 2, 3.
Okay. Now you treat that as if that's a determinant, even though you can't take the determinant of a non-square matrix, but just live with that. Okay, what does this give you? 0, I.
plus 2j
2j
plus 3k
plus 3k.
and then 8k
Second,
8k
plus 8k.
minus 3i
Got it?
0j
Okay. So what does that give us?
negative 3i
All right.
plus 2j
All right.
plus 11k.
All right. There's a vector guaranteed to be orthogonal to those two, if we did it right, and let's hope we did. But that's still not a unit vector. So how do we get a unit vector out of that? Oh, maybe that's at least 2 weeks ago.
On the magnitude?
Divide by the magnitude. Perfect. And what's the magnitude?
The square root of 9 plus 4 plus 21.
Whoa, big number, huh? So that'll be, let's first do that.
Square root of 34.
Square root of 134? I was hoping that would be a perfect square. My hope was dashed, okay? I think it's 135. No, 134, you're right, okay? Yeah. So this will be, to put it, if it's okay with you, I'm going to go back and put it in component form because that's so much easier to write. Minus 3 over root 134, comma, 2 over root 134, comma, 11 over root 134. Now, you don't have to write it that way. You can do it in IJK notation if you would like. I haven't turned my page yet to see how they did it. And let's see, minus 3 over root 134i plus 2, the I, plus 2 over root 134j plus 11 over root 134k. Good for them. They got it. Okay? Now, I'm going to erase this so you can see how they did it. Anyone need it longer? You okay? Okay. So the cross product is going to produce a vector that's orthogonal. And this is what they did. They showed U of V down here. U being 1, okay, here's X, Y, and Z. 1 in this direction, minus 4 in this direction, that puts you right here, and then plus 1 in that direction. So that's going to be about right there. Okay. Hard to visualize this in a three-dimensional figure on a two-dimensional board, but it helps that they put in the cross hatch there. It shows you where this cross with that, cross with it, intersected there, and then you go up from there. This looks like this is on line with that. It's not. This is out here. Okay. And then the next one was 2i this way plus 3j, which would be here. So there's that one. And it's in the XY plane, so it doesn't show any shadowing there. It's in the XY plane. When you cross those two, and you're going to be a vector that's up here, perpendicular to the plane that contains those two, and its components are, well, we had it. Well, we did it, but they haven't done it yet. Negative 3 to 11. Well, that's obviously not a unit vector, but it is a vector that's orthogonal. But u cross v. Now, if you did this, you'd see this is negative 3 in the I direction, plus 2 in the j direction, plus 11, way up there somewhere in the k direction. Okay. Now, oh, and there it is, minus 3i plus 2j plus 11k. There's the cross product, which is a vector, orthogonal to those twos, orthogonal to the plane that those two are in. And now, because the magnitude of that is root 134, and not a perfect square, boo hiss, you can then write the unit vector that's orthogonal to both as the that one. Now, there's no reason to do this, but also if you put the plus here, minus there, and minus there, it would also be orthogonal to it because it's anti-parallel to this one, so it would also be orthogonal. But why do that? There's no reason to. Okay. Now, they're skipping example 3, so before we get to this slide, let's go back and do example 3. Were there any questions on that before we move on? Example 3. The vertices of a quadrilateral are listed below. And then they say, show that the quadrilateral is a parallelogram and find its area. So here's the vertices. Okay, now what does quadrilateral mean? 4 sides, yeah. 4, quad means 4, lateral means lateral sides. So 4 sides. It's a 4-sided figure, and it says this is a quadrilateral, and then we need to show that it is a parallelogram, and we need to find its area. So here are the vertices of the quadrilateral. A is 520. B, I can't write, is, these are points, so these are parentheses, 261. C is the point, 247. And D is the point, 506. Now, these are the vertices of a quadrilateral. It says, show that that is a parallelogram. Now, how are we going to show that's a parallelogram? What does it require to be a parallelogram? Two opposite sides have to be parallel to each other. That's why they call it parallelogram. Okay. So it's also a quadrilateral, 4-sided figure, but the two opposite sides have to be parallel to each other. Now, how are we going to show that they're parallel? Okay, what about the vector? Okay, so you're saying find the vector between these and show they're parallel, and to be parallel, okay, and not only, now a parallelogram, not only are they parallel, but they're equal in length. So if you do as you're suggesting here, we do the vectors represented by these 4 points. Now here's sort of a snag in the problem here, okay? We don't know which of these are adjacent sides. So if you do one vector here and another vector here, you can still do a third vector up here, and none of those 3 are parallel. So you're going to have to do every combination and find out that 2 pairs are equal and opposite, equal and parallel, which if they're equal, they're going to be parallel. So how do you want to begin? Good thoughts on what you're doing, just a little bit of a warning, okay? So what you get? Where are you going to begin?
Vector AB.
Okay, we'll do vector AB. So we're going to start with A, terminate on B. So what would be its, and if y'all are okay with it, I'm just going to write it in component notation. It's easier, quicker. I don't have to write IJs and Ks, you know.
So we do, if it's vector AB, we do the B1 minus A1.
That's it, yeah.
Okay, so negative 3,
-3, comma,
4,
4, comma,
and
1. Okay. What two you want to do next?
1.
I really don't
A and
care.
C.
Huh?
A and C.
A and C. Okay. Now I know that those aren't going to be opposite sides because they have a common point A. So, but we can still do those. So let's do AC. But and what would that be? -3, comma, 2, comma, 7, comma. Okay. Pick another two.
BC.
BC. Okay, before, never mind. BC. That would be 0, comma, -2, comma, 6. So far, not looking very promising, is it? Okay. Give me another. AD. Okay. And, okay, what would that be? 0, comma, -2, comma, 6. Ding, 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 ding. We have a wiener here, don't we? Okay. We've got two of these are parallel. That doesn't guarantee it's a parallelogram. You can have two, well, wait, it does, doesn't it? Almost. If they were parallel but not equal in length, that would be a trapezoid. Okay, could be a trapezoid. These are parallel and equal in length, but I still think you probably need to show that the other two are. Now, if these two, BC and AD, are parallel and equal in length, what is the other pair that had better be? BC and AD are equal in length, so it better be
A and CB.
Say again?
DA and CB.
C, A, and BD. Okay. We already did CA sort of. We did AC. So let's do BD and see what we get. Or whichever you choose. Which you choose? BD or DB? BD. Okay. And what do those give you? 3, comma, -6, comma, 5. Did we do that right? Whoops. That didn't seem to work. That must be the diagonal. Okay, so it looks like we're going to have to do the other. And what would that be? The only combination we haven't done.
C and D.
Say again?
C and D.
C and D. Okay, let's try CD. Is that the order you wanted? Okay, and what would that be? 3, comma, -4, comma, -1. What do we have here? Exactly the opposite of that. So all you have to do is do either DC or do BA. So yes, we got two sides that are equal and opposite, and another two sides that are equal and parallel, and the other two sides equal and parallel. Yes, it's got to be a parallel. These two that were nothing those are your diagonals, okay? They didn't give you anything. Okay. Now, that was the first part. Show that the quadrilateral is a parallelogram. We've done it. Find its area. Do you remember what the area of a parallelogram is?
Magnitude of U dot B.
It's the magnitude of,
The adjacent sides.
okay, but what did you say?
U cross B.
Use cross V. I couldn't hear whether you said dot or cross. So, what is it going to be? Magnitude of AB cross, second, AD, that would work. Okay. All right, because these are two parallel, those are two parallel, that means these are two adjacent sides, so let's do it. And let's first do, I guess, I'll do the magnitude of the, whatever you call it, determinant of, and what do you have there? How do you do that? Okay, wait, I, J, K, I, J. Next. -3, 4, -3, 4. Okay, lots of lines here. Next. 0, wait, yeah, 0, -2, 6, 0, -2. Okay, I haven't drawn my lines very nicely. Okay, where do we begin? What's that give us? 24I. Okay. Plus 6K. Next. 0K. That's all we needed was 2 more of those, okay. And all right. Looks like we got some big numbers in 26I plus 18J plus 6K. All right. Now what we need to do is the magnitude of that, which would be, pull out the calculators, folks. What? Okay, 26 squared plus 18 squared plus 36. Okay.
I got 32.19.
Okay. Let's see what they got. Oh, look at that. They did too. Approximately 32.19. The area of that parallelogram. Okay. Now they showed the graph of that, and that looks awfully close to being a square. It may or may not be. It may not even be a rhombus. In fact, it probably looks like it's not. But it's hard to tell because you've got foreshadowing going on there. It's just really hard to see. Okay, good deal. Any questions on that? Okay, let's move on to back to our, in physics, the cross product can be used to measure torque. That's the moment M of a force about a point P. as shown in this figure here, okay, 1139. If a point of application of the force is Q, then the moment of F, that force F, about P is the moment, and they bold it, they put it as a capital too, for some reason, the vector PQ, because it always starts with the point going to the application point, that is always initial to final, cross with the force, the magnitude of the force. Now, any of you ever use a torque wrench? To know you are using a torque wrench?
Is it that one that kind of spins?
Yeah, and it has an indicator near the where you fix it on the lag. For instance, when you're doing the lag nuts on the wheel of a car, you're supposed to get them to a certain torque, okay? Make sure they're tight enough, okay? A torque wrench will tell you whether you got it that tight or not. So you put the lag nut wrench on the lag nut right there, and you push in this direction. Here is the length of the handle of that torque wrench, and you're pushing on this end, trying to tighten around there. So twisting force is a torque. Okay, so it's PQ cross F. Okay, remember which way you do it. PQ cross F. So that would be PQ cross F. So your torque here would be up. And there it is. There's the torque up. Now, they say the moment. I'm used to having a capital tau there representing torque. They're calling it the moment. The magnitude of the moment, M. Now here they put times New Roman M. There's a Arial M. I don't know why they changed, but it's the same thing. Measures the tendency of the vector PQ to rotate counterclockwise using the right-hand rule, because you're pushing that way, about an axis directed along the vector M. Okay? And notice that the M is perpendicular to both of those. Now, to get maximum torque, you want this to be perpendicular to that. That's how you get your maximum torque. If you do it at an angle like this, you're not going to get as much torque. Maximum torque is when those two vectors are perpendicular, then you get the maximum moment of torque. And it seems like to me they've skipped example 4. So let's go back and erase all this. Anyone need this any longer? Okay. And let's do example 4 here. A vertical force of 50 pounds, they showed it vertically downward, is applied to the end of a 1-foot lever that is attached to an axle at point P, which they put at the origin, shown on the figure at the origin. Find the moment of this force about the point P when that angle theta is 60 degrees. Okay? When they say moment, the indication there, that is a vector. I was sort of anticipating them to say the magnitude of that, but they didn't. They say find the moment of this force about that point when theta is 60 degrees. Okay. Now, notice what units we're using.
So it's
Pound, that's going to be a the force is in pounds, the distance is in feet. So this is U.S. customary. Used to call it the British system, but the British technically don't use it, or officially don't use it anymore. So So it'll be in foot-pounds. Now, if you remember, work was in foot-pounds when we did dot products. These are different foot-pounds. One is same direction force, the other is somewhat perpendicular in the force. That gives you the moment. Okay? So how are we going to do this?
We need to get vector PQ.
Say again?
So don't you have vector PQ?
Okay, vector PQ. And what would that be? PQ. Now, I probably need that in,
1 foot.
okay,
There's no I, right?
okay. That's exactly, that's the observation I was looking for. The way I understand that they've drawn this, they've drawn the PQ in the XZ plane, because they said the force is downward, and like I said, it appears that the P is at the origin, so I don't think we have any choice but to say you're in the YZ plane here. So we need to identify that. That would be 0I. Now, what would be your J component?
Sine theta.
Sine of the 60. Is that right? No. The J component would be the cosine of 60. That in the same direction of that, the adjacent side. What's the cosine of 60? 1/2. There's your J component.
So this one is the,
What's that?
so the K is the sine.
And K would be the sine, and what would that be?
3/2.
Root 3/2. So there is your PQ vector. What is your F vector? -50, right. And that would be in the K direction. So that would be 0, 0, -50. These are in feet. Those are in pounds. Okay? And the moment would be PQ cross F, which would be IJ. I can't write IJ. Zero. Got it? Okay. Now, as Patrick, I think, has already observed, your moment has to be in the I direction, okay? Because the other is in the XZ plane, so this has to be in the direction of the X vector. And sure enough, here we get it right off the top. What is that? -25I. And then when you do the others, you get 0, 0, 0, 0, 0. So it would be -25, which means going back in the other direction. And sure enough, if you put the fingers, okay, right hand, fingers up in the direction of PQ, and Z down, yep, -I. And that better be what they got. Yep, negative. The magnitude of that moment is 25 foot-pounds, but the actual moment is -25I.
And
Good.
it becomes positive because it's squared and it's square root. Right?
What's that again?
It
Yeah.
becomes positive because you square it. and
Yeah,
it's
a
square
magnitude's
root.
always positive. Yeah, you're absolutely right. So it's the absolute value of that. Yeah. Okay. Now we go to yet another kind of an application, you might say, and that's the triple scalar product. Okay? Now, triple scalar product, if you remember back, figured I was going to wind up eating my words. I think we're back at number 6 when I said I don't remember ever using that. Well, I think we're going to use it now, okay? I had forgotten about this. That is the definition of a triple scalar product, okay? For the vectors u, v, and w in space, the dot product of u with v cross w is called the triple scalar product, and guess how it's defined? You do the same thing you did with crossing u, v, and w, except instead of the ijk at the top, you put the components of u. And then when you do the determinants are always, now when you had ij and k there, it came out being a vector. Now it's going to come out being a scalar. That's why they call it a triple scalar product, because the dot product between a vector and the cross of two vectors, which is a vector, is always going to be a scalar. So there is your definition for your triple scalar product. Okay? So, if the vectors u, v, and w do not lie in the same plane, then the triple scalar product of u dotted with v cross w can be used to determine the volume of the parallelepiped. Okay, boy, that's a nice one. That's a polyhedron, all of whose faces are parallelograms. Okay, with u, v, and w as adjacent edges. So this is u, v, and w. That way, as adjacent edges shown here, you can get the volume by this triple scalar product. Now, the area of a base is v cross w. Remember, that's the area of that parallelogram. Okay, the magnitude of u cross w, v cross w. And then you dot that with u, okay, and you get the volume of the parallelogram, okay? Because in reality, what you're doing, to dot this, you're taking that base and then doing the the perpendicular component to it. In other words, you're sort of just straightening this parallelogram here, straightening this up. And I don't know if you remember, goodness, or maybe you haven't got there yet. I think we did in trig, didn't we? Pappus theorem, that if you have any column, no matter how you stack them, the volume's the same. So just think of a stack of quarters, and then tilt them some. Still the same volume of quarters. Well, that's what we're doing here. You've just gotten this thing and tilted them. This height was what you had if you straightened that up. You would have the same volume. So anyway, that's what's going on there. The dot product would straighten that up. Okay. So, theorem 11.10, the geometric property of this triple scalar product, the volume V of a parallelepiped with vectors u, v, and w as adjacent edges is the V would be the absolute value of u dot v cross u. You need the absolute value bars there because there's nothing here that tell you got the right orientation. You could come up with a negative. Well, volumes are never negative, so you just take the absolute value of it. All right. They did a proof here. I'll let you look at that proof. I'm sure it's going to be a lot of fun. Let's do example 5. Here it is. Find the volume of the parallelepiped, I love that word, okay, Lots of L's and P's in it. One R, okay. Shown in this figure, having U being 3I minus 5J plus K, V being 2J minus 2K, and W is 3I plus J plus K as adjacent edges, okay? Now, kind of the beauty and the magic of this is it doesn't matter which order you do it, okay? They tell you these are the adjacent edges, so we take their word for it. And then what would be the volume? Okay, it's the absolute value of, now this is sort of tough to do because absolute value symbol and the determinant symbol are the same. So, the absolute value of, the determinant of, what would you put where? Okay. Again, it doesn't matter which one you do where, you just do them. Okay? You can put U on top, V on top, W on top, it doesn't matter. I just do them the way they show them. 3, negative 5, 1, 3, negative 5. Next. Zero, 2, negative 2, 0, 2. Next. 3, 1, 1, 3, 1. Okay, we're going to take the determinant of that and then do the absolute value of that determinant. Same symbol, sorry. So what will this be? 6 plus what? 30. All right. Negative what? Negative 6. Plus 6. 0. Okay. So the 6 minus 6, that adds a 0. So this gives you 36. I hope. Yes, look at that. Okay. There is your volume of that parallelepiped. Now, a natural consequence, let's see, maybe they're going to show that. Yeah, well, let's let them finish this. Do you need mine up there anymore? Okay. So by that theorem, you can have the volume is the absolute value of those, which is, they left off one absolute value bar, the determinant of those 3 vectors written in that way, and then they did it this way, and then you have to remember where to put the minus signs and that kind of stuff, and that gave you 36. 12 plus 30 minus 6. 42 minus 6 is 36, yeah. Now, a natural consequence of that theorem is that the volume of a parallelepiped is 0 if and only if the 3 vectors are coplanar. If they're in the same plane, then they don't have any height to them, okay? That is when the vectors U, U1, U2, and U3, vector V, V1, V2, and V3, and vector W, W1, W2, and W3 have the same initial point. Wait, the others did. They lie in the same plane if and only if that determinant is 0. Okay? And so if they have the same initial point, you need them to have the same initial point. And if those three are in the same plane, then the cross product would be perpendicular to the U is the one we've been using, and that would mean they're all three in the same plane. Okay. That is the end of 11.4. Okay. Homework exercises here. 3 or 5, they're both a Calc Chat. 7 or 9, both a Calc Chat. 7's a Calc View. 11 or 13, both a Calc Chat. 15 or 17, both a Calc Chat. 15's a Calc View. 19 or 21, both a Calc Chat. 23's a Calc Chat and Calc View. 25's a Calc Chat only. 27, okay, any of the odds, 27 through, well, 27 or 29, either of those two, both a Calc Chat. 31 or 33, both a Calc Chat. 31's a Calc View. 35's at both Calc Chat and Calc View. 37's a Calc Chat. 39 and 41, you can explore doing either one of those. They should be at Calc Chat. If they are, you can follow up on them. 43 or 45 are true-false. They should be at Calc Chat. And then there's a couple of proofs. I think these are the ones I said you might see later. 47, any of the odds 47 to 51. And then there's another couple of proofs, 53 and 55. That's up to you. I know at least one of you is a math major. I don't know how many proofs you'll be doing, but some of these may be worth your while to look at. All right. So let's end that. And someone let me, well, let's see, I'll see in just a minute. We're at 156 and we go to, when did we start? 12:30 to 2:10. And then so we've got 14 minutes. Okay. So let's get started on 11.5. And earlier today, PowerPoints were taking forever to load, but this wasn't too bad this time. So we go from current slide. And we're still in Chapter 11. I don't know. I know it looks like maybe one of you is looking at a phone. Are you looking at weather by any chance?
No. He's
Huh?
not. He's not.
He's not.
But I,
You are.
yeah.
How are things looking?
February the 5th, I believe there's going to be, I would imagine, what's the
The 5th.
No, I think it was the 7th, because I know that's when my sister, basically they're shutting down things in Jefferson County.
Say
So
that
the
one more
7th
time.
and the 8th, I know for the 7th, everything is pushed back 2 hours, and I think the 8th, they're going to cancel.
Okay, so it doesn't look like we're going to have the bad weather as early as what they were saying earlier. Is
How
that?
early? Oh, today?
Yeah, that's what I'm asking.
Oh, yeah, everything extracurricular is shut down too.
Okay, wait, have they already done something?
Well,
No.
as far as Jefferson County, what do you mean?
Oh, Jefferson County.
That's what I'm talking about.
Okay, Jefferson County has done what?
7th, they're not going to school till 10 a.m. And then Friday, I think they're out. And then today, all extracurricular activities they put a stop to.
After school, okay.
Yeah.
All right.
So after school, you should. After this, you should go home.
No. Okay. I've got 2 more classes after this. That's what I was asking about. So nothing from the school yet, but nothing about the weather being here. At one time, they said it sounded like they were going to say early afternoon, as maybe as early as 4, but they're not saying that now. Okay.
Our church got canceled for tonight.
What's that?
Our church got canceled.
It did. Okay.
Maybe I suggest you go home. That's what I'm saying.
Okay, it's not a bad idea if you don't have any more classes, but I'm asking if classes, because I've got classes, and I'm not going home if the classes are supposed to meet. Okay. So, Chapter 11, we're still in vectors and geometry of space. 11.5 is lines and planes in space. Our objectives here is to write a set of parametric equations for a line in space. Okay? Write a linear equation to represent a plane in space. Sketch a plane given by a linear equation and find the distances between points, planes, and lines in space. Okay. Those are our objectives here. Let's start with lines in space. No tigers, never mind. Okay. In figure 1143, this one right down here, consider the line L. Here's the line L up here. Just somewhere up there in space. Okay? Through the point P, x1, x, y1, z1, and point Q, which we don't put any subscripts on. That means that's your variable point. It's through line P going through some point Q, through point P, or a given point P going through some unidentified point Q. But it's parallel to this vector down here, which is ABC. Okay? Meaning it's A units in the x direction. That looks like maybe 1 unit here, 2 maybe, I don't know, something like that. B units in the y direction, and then C units up. Okay? So this is coming somewhere out here in the first octave. Okay? So, we want our point, we know the point P is fixed, but we want the vector P, or the line PQ, to be parallel to this given vector V. Okay? The vector V is a direction vector for the line L. The A, B, and C are called direction numbers. These are all good terms to hang on to. You're going to see them later. One way of describing that line L is to say it consists of all points Q, X, Y, and Z, for which the vector PQ, P being fixed, is parallel to that vector V. Okay? All we know about V are its components, A, B, and C. So notice these are vector components. These are coordinates of a point. Okay. And the P is parallel to this, PQ is parallel to this, meaning it's some multiple of this vector here. Okay? P being some parameter which makes that true. Okay? That means that PQ, as I was just saying, is a scalar multiple of V. So you can write like they did, PQ is some scalar T times V. Now one problem here, it looks like they bolded that T. You don't bold scalars. That's not bolded. That should be what they have here. T is not a bold, it's a scalar. Okay? Some real number. Okay? Where T is a scalar. Now, what does that mean? PQ, remember, is from a fixed point P, that's always the second point here. Q is your variable, x, y, z. So that means this is x minus x1, comma, y minus y1, comma, z minus z1, is equal to some scalar multiplied by the vector v. Vector v is components a, b, c. So you just multiply a times t, b times t, and c times t. It doesn't matter which order. I would have said ta, tb, tc, but it doesn't matter. Those are just numbers. Okay? And that is the t. Now this time they put the t in regular, not bolded. See, this shouldn't have been bolded. Okay. Doesn't really matter. By equating the corresponding components, you obtain a parametric equation for a line in space. In other words, x minus x1 is equal to at, y minus y1 is equal to bt, z minus z1 is equal to ct. Okay? Now, if you wanted to rearrange those slightly, you could say x is equal to at plus x1, y is equal to bt plus y1, and z is equal to ct plus z1. So that's how I'd probably write them, because that gives you your x, y, z. Okay? Parametric equations of a line in space. They each have a parameter, same parameter associated with it. So here's your theorem 1111. Parametric equations of a line in space. A line L parallel to some vector ABC passing through the point P, and the vector is passing through the line is passing through the point x1, y1, z1. Okay, is represented by these parametric equations. X is equal to x1 plus at. That's what we did. X1 plus at. Y is equal to y1 plus bt. And z is equal to z1 plus ct. I would have written them in the opposite direction, but that's okay. So the direction numbers A, B, and C are all, now if the direction numbers A, B, and C are all non-zero, then you can eliminate the parameter t in the parametric equations and obtain symmetric equations of the line. So here's what we're going to do now, going backwards on it. In fact, I would say go back to this stage, okay, and do x minus x1 over at, no, over a is equal to t, right? That's not quite right. That's not quite right either. Okay. Let's just do it back the way they did. Okay. X minus x1 divided by a. That would be x minus x1 divided by a. Yeah, we could go back to that of it. That's equal to t. Y minus y1 divided by b is equal to t. Z minus z1 divided by c is equal to t. So therefore, x minus x1 over a is equal to y minus y1 over b is equal to z1 minus z1 over c, because they're all equal to t. Now, this shows, remember, this indicates neither a nor b nor c could be 0, because otherwise you can't do this, okay? You just can't do it, because you can never divide by 0. So all your direction numbers have to be non-zero for this to work. They don't have to be non-zero for that to work. Okay. Keep thinking. Yeah, if you had said x minus x1 is equal to at, that's what I was trying to do before. Just forget about these two for a minute. This is equal to that divided by a. This is equal to that divided by b. This is equal to that divided by c. That's what I said. Easier to do from that point. Okay. Now, here's example 1. Bottom of page 787. How are we doing on time?
3 minutes.
10 minutes?
3.
Oh, 3 minutes. Okay, let's see if we can get this done. Find the parametric and symmetric equations of the line L that passes through the point 1, negative 2, 4 is parallel to this vector 2, 4, negative 4. Okay? Anyone make a stab at the parametric equations? I'll go back real quickly. I thought I was going to go back real quickly. There we go. There's the parametric equations. Okay, what would that be? I'll start it. X equal. One. Okay. Plus 2t, right? Right? Y is equal to? Negative 2 plus 4t. Z is equal to? 4. Second? What about it for minus 4t, right? Okay? Now, those are your parametric equations. Okay? X, Y, and Z. Now, what are your symmetric equations?
X minus 1.
Over
2.
2 is equal to
Y plus 2.
over
4.
is equal to
Z minus 4.
Z minus 4 over negative 4. So you could have said that last one to be minus Z plus 4 over 4 if you wanted to. It doesn't really matter. Okay? Now, they haven't quite done this yet, but I don't see why they don't. Here would be any point x, y, z on the line you could write as 1 plus 2t, comma, minus 2 plus 4t, comma, 4 minus 4t. Plug in a t, any t, you'll find the point on that line. Okay? Let's see how they did it. Find the set of parametric equations. X is equal 1 plus 2t, perfect. Y is equal to negative 2 plus 4t, perfect. And z is equal to 4 minus 4t. Yes, perfect. Your symmetric equations then would be, and they kept it in the first form, x minus 1 over 2 equal y plus 2 over 4, yes, equal z minus 4 over negative 4, or minus z plus 4 over 4. Doesn't matter how you do that last one. Because A, B, and C are all non-zero. Oh yeah, we already did that. All right, we'll start next time. Well, let's see, where will we start? That was example 1. We're going to do example 2 next time. We won't start with planes yet because we've still got to do example 2. Good deal. Be safe in the weather. Whatever happens, keep your ears out for that. You've got physics tonight, right?
Yeah, it's at 2:30.
2:30, yeah. So you'll probably be okay with that. All right, good deal. Any questions? Have a good week. Well, I'll see you tomorrow. Okay, but the rest of you have a good week. You can still have a good weekend, but I'll see you tomorrow. I'll see if I can do something about making, never mind, okay.